Hey everyone, welcome to lesson number 1 of Unit 8, which is on quadrilaterals, and our lesson today is going to be on parallelograms. So what is a parallelogram? A parallelogram is a quadrilateral that has both pairs of opposite sides parallel. Makes sense, right? Parallelogram, parallel sides. Quadrilateral, by the way, if you weren't aware of this, it's just a shape with 4 sides, or a polygon with 4 sides. Okay, so here we have a 4-sided polygon, and in order to make this a parallelogram, we need to show that both pairs of opposite sides are parallel. Hopefully you remember that the symbol for parallel is little triangles. Okay, so if I want to show that one pair is parallel, I'm going to use the same number of triangles, which is why I drew 2 on that particular pair. And then I'm going to draw only 1 on this one. Okay, so now I have both pairs of opposite sides parallel. So this fits the definition of a parallelogram. We have a couple of interesting theorems that work directly with parallelograms. Our first theorem is going to be that opposite sides are congruent. Our second theorem is that opposite angles are congruent. And our third theorem is going to tell us that the diagonals bisect each other. So I've actually drawn in the diagonals right here for us, right? They go from one angle to the opposite, so it's a line segment. Again, we have a diagonal here. So let's look at each of these theorems on our parallelogram. We're not going to prove this here, by the way. They're easy enough to prove, but we're going to do them in class instead of here. Okay, so if you don't believe me about this, you can find a proof somewhere else online, for all I care. Okay, so let's mark our picture according to what this tells us. Opposite sides congruent. So not only do we already have opposite sides parallel, which is the definition, so we know that this is a parallelogram, but we want to show that opposite sides. So how we're going to do that is with the little dashes. So I'll put 2 here. Okay, this particular side, or these 2 sides, are going to be congruent to each other because they have the same number of markings. And here I'm going to put 1 on each, showing that these both have the same number of measures. Then we have opposite angles. This full angle here and this full angle here are opposites, right? They're across from each other, and according to this theorem, they're going to be congruent. And I can do the same with this full angle here and here. They're opposites, thus they are congruent. And then we have this last thing, right? The diagonals bisect each other. We'll do that in light blue. So this diagonal, this segment, is being cut in half by this one. That means we get 2 equal pieces out of it. And then same thing's happening here, right? This segment is being cut in half by that one. So now we have 2 new equal pieces. Okay, so we have a lot of marks going on this parallelogram, but each of these things on their own, whether it's the opposite sides congruent, angles congruent, or diagonals bisecting, each of those on their own is enough to prove that we have a parallelogram. Okay? Now, I'm going to talk about something real quick with parallelograms that's going to make more sense in the second lesson, but I'm still going to introduce the idea to us right now. Okay? I want everybody to think of a parallelogram as like the granddaddy shape. Okay? Anything that's true for a parallelogram is going to be true for any shape that is a type of parallelogram. And in our next lesson, we're going to be talking about special quadrilaterals that are all types. So, when you hear me talk about granddaddy parallelogram, all of these traits, all 4 of these things, are going to be true for anything that's considered a parallelogram. So keep that in mind for the second lesson. But for right now, we're going to just focus on using these to answer some questions. Okay? So, this is what type of problems you'd be most likely to encounter in the wild, right? We have a shape right here that Part of it definitely looks like a parallelogram. We know because it fits the definition. We're trying to solve for x and y, which look like they're angle measures. And then we have the only piece of information given to us outside the parallelogram. Well, does that really matter that it's outside? I don't think so. Right? We know that we have a straight line right here, which is worth a total of 180. So we're working with supplements. So if I take 180 and get rid of the piece I already know, it's going to tell me what I'm looking for is worth 140 degrees. Okay. At this point, I have enough to solve for one of my variables because we know opposite angles, oops, that's not on the screen. We know that opposite angles are congruent. So I can see x in this 140 that I just found are opposites. That means x equals 140 degrees. Now we want to figure out y. There's a bunch of different ways that we can figure out y. I'm going to show you one that works directly with the definition of parallelogram. We have parallel lines here, right? And we have this line that cuts through both that we call the transversal. What I'm noticing, and I'll highlight it in orange right here, is that this angle right here and this angle right here are corresponding, right? They're in the same position relative to their intersection. And if they're corresponding, we know that they're equal in measure. So this angle down here is going to be worth 40 degrees. Are there other ways we could have found that? Sure. We could have done a lot of stuff. But for right now, I think the corresponding angles is the easiest to work with because it fits our definition of parallelogram. Anywho, we're still trying to solve for y. So we need to look at, again, opposite angles that are congruent. We can see that these are across from each other. They're opposites. So I now have y equaling 40 degrees. Here's a problem right here to try. It's not necessarily the exact same process as the past one. You could be using any of these theorems to help solve. So go ahead and try this one out and pause it and resume when you're ready to check your solutions. Alright, let's see. I'm going to get rid of the theorems from the screen, so hopefully you have those written down somewhere. Okay, what I see here is a triangle, actually two of them, that are inside of this parallelogram. Well, good news. If I have a triangle, I can figure out my missing angle measure by adding the two that I already know and subtracting from 180. Right, so 50 and 60 is 110. 180 minus 110, that's 70. So we found this angle right here to be 70. Alright, but why do we care about that angle? Because we know opposite angles are congruent. And these right here and here are our opposite angles. So we found y to equal 70 degrees. That was coming from one of these theorems, right? Theorem 2. But if we want to find x, we're going to do a little bit differently. For x, we should notice that we have parallel lines being cut by a transversal. And we have an angle measure here of 60 degrees. That is an alternate interior to angle x, which is right here, right? They're on the insides, which makes them interiors, and they're on opposite sides of the transversal. So we have alternate interior angles. We should know at this point that alternate interior angles are congruent. So we can say that x equals 60 degrees. That did not come from these theorems. That came from the definition of parallelogram. So hopefully you're starting to observe that the theorems and the definition are all very useful in helping us solve parallelograms. We have one or two more examples. I don't remember. Two more examples for us to look at. Okay. Our first example. We want to solve for x. Okay, and if you're having a little bit of difficulty reading this, this says 12x minus 3, and this says 7x plus 22. Okay, and we have, it's a little blurry, but these are the double triangle marks, single triangle marks. So we have a parallelogram. That means we can use some of our theorems, right? And what I'm noticing here is that we have diagonals. Well, there was only one theorem that talked about diagonals of parallelograms, and it said that they bisect each other. So I've got this one here that's being cut in half. So that means that these two pieces should be equal. Right? They're equal to each other. Alright, so if I want to solve for x at this point, I just take those two pieces, 12x minus 3, set it equal to 7x plus 22, and solve for x. I'll subtract 7x from both sides. So 5x minus 3 equals 22. We'll add 3 to both sides. So 5x equals 25. And then we'll divide by 5. And we find x equals 5. There's an ugly looking 5. Okay, anyways. Pretty simple, right? Diagonals bisect. We know what bisect means, so we just put 2 and 2 together to get our solution. So there's one more of these problems for you to try. It's really not a lot of algebra necessarily. This is just thinking about definitions and theorems. So is this a parallelogram? And then why or why not? I'll give you a second to think about it. You don't even have to pause the video. What do you think? I'm thinking no, personally, because here are my opposite angles, and they're two different values, right? 38 and 36. If this was a parallelogram, they'd have to have congruent opposite angles, but they don't. So that means that this line is probably a little bit more steep, and this is just slightly more shallow, so they're not parallel. This is not a parallelogram. That's really it for the parallelogram lesson. We're going to be talking about other types of special quads, which are going to be types of parallelograms in lesson number 2. So I know I talked about granddaddy parallelogram before. Keep that in mind. If you have any questions about what happened in this video, bring them with you to class or leave them in the comment section and we'll do what we can to answer them. Alright, have a great rest of your day.